Welcome to HEATHKIT Continuing Education. Education has always been one of Heath's basic business philosophies. We believe that there is a substantial amount of knowledge to be gained by building any HEATHKIT. Part of the fun and satisfaction of assembling a kit is in learning how it is made, how it operates, and how it is used. Now, HEATHKIT Continuing Education takes this philosophy one step further by offering formal individual learning programs such as the one you are about to begin. This individual learning program is designed to teach you a specific subject in the shortest time for the lowest cost. But before we give you more details about this program, let's consider the concept of continuing education and its importance to you. Continuing education is learning that you receive after you complete your regular formal education in high school or college. It includes all of those special programs designed for self-improvement and recreation. There are a wide variety of continuing education programs available to you. These include short evening courses given in many high schools and community colleges, conferences and seminars sponsored by universities and professional associations are also a form of continuing education. Another category includes those special training programs given by your employer for improving your job performance. Home study courses are another form of adult learning. Continuing education also takes in those less formal activities that you often participate in to improve your knowledge. For example, pursuing a related hobby or reading pertinent magazines and books are excellent methods of independent learning. Earlier in this century, continuing education as we know it today basically did not exist. It was not the necessity that it is now. In those days, your high school or college education usually provided all of the knowledge necessary to permit you to perform satisfactorily on the job or to satisfy your intellectual interests. Today, things are different. Technology is changing at a phenomenal rate. This makes it especially difficult for those of you working in science and engineering to keep up to date. Ideas and knowledge that were valid yesterday are obsolete today. New components, techniques, and equipment are being developed daily. The result is rapid obsolescence of your technical knowledge. Your formal education now provides only a framework or foundation of basic knowledge on which you should build. You must rely on continuing education to periodically update your knowledge and renew your technical skills. All trends seem to indicate that this rapid change and explosive technical expansion will continue. In fact, there is every sign that it will actually accelerate. For that reason, it is essential that you participate in some form of continuing education. It will help you to cope with the changes that are taking place. And it will help you to maintain your competence and increase your effectiveness. Today, self-improvement through continuing education is a practical necessity. You must anticipate future changes and plan on a lifelong program of learning. As you will discover, your success on the job is tied directly to your technical competence. Continuing education will help ensure that success with renewed knowledge and confidence. Many individuals also participate in continuing education for pleasure. A course may be hobby-related, or it may simply be a leisure time pursuit that satisfies a personal curiosity. Learning is fun, and some people consider it an end to itself. Continuing education will also keep you up to date on things happening in the world, and will permit you to understand what's going on around you. It can help you make more intelligent decisions and can make you more interesting to others. HEATHKIT Continuing Education was established to fulfill the need for knowledge in the various technical fields. HEATHKIT individual learning programs can help improve your job performance by giving you new knowledge and skills. They can also enhance the enjoyment of your hobby, make you a more intelligent consumer, and stimulate your interest in a favorite subject. HEATHKIT individual learning programs were made for those of you who appreciate the importance of continuing education. If you find learning a pleasure and like to do things for yourself, you will enjoy this program. The individual learning program that you are about to take is a self-study course. It was designed for your personal use. With this program, you can learn the subject with little or no outside help. The material has been carefully prepared and validated to ensure that learning does occur if you complete all of the activities provided. The knowledge in this course will become yours through your own independent efforts. There is a significant trend toward the increased use of independent instruction techniques in all areas of education. It is a proven fact that the things that an individual learns best are those that he reads and reasons out for himself. Most solid learning comes primarily from your personal participation in directed learning experiences. This program organizes and facilitates your individual learning efforts. Each HEATHKIT individual learning program is also multimedia in nature. This means that we use a variety of teaching methods that not only guarantees learning, but also makes the program more interesting and fast-paced. The course is both efficient and effective, and we believe you will be pleased with the results. We hope that you will make continuing education a regular part of your life. It is one of the few things available to us that is both entertaining and beneficial. Enjoy your program and put your new knowledge to work as soon as you can, for it is only through the application of your learning that you will be rewarded. Best wishes for your success and happiness from those of us here at HEATHKIT. Before you get started with this program, we'd like to tell you more about it, specifically how it is organized and how you should use it. With this information, you will be better prepared to take the course and therefore will get more value from it. Each HEATHKIT individual learning program is made up of 6 to 10 separate lessons that we call units. Each unit covers a specific topic within the subject area. A unit begins with a short written introduction and a set of objectives. The unit objectives state exactly what you will learn. Next, a unit activity guide lists the various learning activities presented in the unit. The unit activity guide recommends a specific study schedule. You should record the time that it takes you to complete each activity in the spaces provided. The first activity in most units is to play an audio record like this one. The record is designed to give you an introduction and general overview of the subject to be covered. Be sure to play this record first, as it will put the subject into perspective and prepare you for the material that follows. Next, you will begin to read the various sections in the unit. After each major section is a self-test review. This is a set of questions that will help you to review the key points in the section and permit you to practice the various problems. Be sure to work all of the problems and answer all of the questions. They are essential to your learning and to your retention of the material. Try to complete the self-test review right after you finish reading the section while the information is still fresh on your mind. Also, don't hesitate to look back through the section to locate a key fact or verify a procedure. Any rereading or reviewing you do will only further reinforce your learning. Some units are presented in a programmed instruction or PI format. Here, the information to be learned is divided up into very small segments called frames. Each frame contains a complete idea, thought, or fact. A question in each frame permits you to use the information you have just read. By dividing the material to be learned into small pieces and testing you on it immediately, you learn it faster and better. PI is a very effective learning method. Throughout each unit, you will also find experiments. These experiments are designed to give you practical hardware experience. You will construct circuits, verify their operation, determine their characteristics, and troubleshoot them by making a variety of tests and measurements. In other words, you will put theory into practice. The experiments back up and reinforce the material that you read elsewhere in the unit. If you have difficulty with an experiment, chances are you have made a wiring error. It is easy to interconnect the components incorrectly, so double-check your wiring for each experiment. All of the parts called for in the experiments are provided with this program, but you will need the HEATHKIT electronic or digital design experimenter and some test equipment. We will give you specific details on this later. When you complete the entire unit, you will then take the unit examination. This multiple choice test enables you to review the most important parts of the unit. It will ensure that you have met the unit objectives. The unit exam is an open book test, so don't be afraid to look back into the unit to get your answers. This exam is another important learning activity, so be sure to complete it. And don't look at the correct answers that follow each exam until you answer all of the questions. When you finish the exam, check your answers and review any that you missed. Then go on to the next unit. As you are working on each unit, try to limit your study sessions to about 1 hour. This will usually give you enough time to read one section or run an experiment. Study sessions longer than an hour are generally less effective because most people get tired and their minds begin to wander. You will not learn well under these conditions. As a result, it is best to have many short study sessions instead of a few long ones. It is also important that you study regularly, at least once a day. Try to make your study sessions a daily habit. You will complete the program sooner this way, and your learning will be more effective. If you spread your study sessions too far apart, you will forget key facts and end up spending a lot of time reviewing. When you complete all of the units, you will have met the course objectives. At this time, you will have the knowledge and skills that you set out to obtain. No further study is required. However, there is one additional thing that you can do. Take the final examination. A comprehensive final exam is supplied with each HEATHKIT individual learning program. You are not required to take it. But the final exam is an important additional learning activity. It will give you a thorough review of all of the most important topics covered in the course. The final exam gives you the opportunity to refresh your knowledge and help ensure your retention of key facts. We urge you to take it. Another reason for taking the final exam is recognition. We are sure that you will want to receive some recognition for the effort you have given to completing the course. If you take the exam and make a passing grade on it, we will award you an attractive certificate of achievement. In addition, you will also receive continuing education units of credit. The Continuing Education Unit, or CEU, is a nationally recognized method of measuring and recording your participation in formal adult continuing education programs. One CEU represents 10 contact hours of participation in an organized adult learning program given under responsible sponsorship, capable direction, and qualified instruction. You will be awarded an appropriate number of CEUs based upon the average minimum completion time of each program as determined by HEATHKIT Continuing Education. While CEUs are not applicable toward a college degree, they are still an important development in adult education. Employers are rapidly adopting the CEU as a way to measure an employee's participation in training. Some professional associations award CEUs for courses they sponsor. Many colleges and universities also award CEUs for adult continuing education courses. All awarding institutions maintain a transcript file where a record of your participation in a program is kept. The CEUs may be transferred to other institutions, companies, or organizations. Complete details for taking the final exam and receiving the certificate and CEU credit are given in the final examination kit supplied with this program. The hardest part of this course is getting started. You will find that the course is fun and interesting once you get going. Give it all that you've got to overcome the inertia that keeps you from taking that important first step. And once you get going, keep going. Let the inertia work for you instead of against you. Then follow through with the final exam and get the credit and recognition you deserve for your work.
You are now ready to begin your HEATHKIT individual learning program on digital techniques. This program is designed to provide you with a thorough background in digital fundamentals. You will learn the binary number system, logic circuit operation, digital methods, and their applications. When you complete the program, you will be able to design and apply digital equipment using modern integrated circuits. To be more specific, we have outlined the goals of this program in the list entitled Course Objectives, located in the front of your manual. Refer to this list now as we review these objectives with you. When you complete this program, you will be able to, number 1, discuss the advantages and benefits of using digital techniques in electronic equipment. Number 2, name the major applications of digital techniques in electronics. Number 3, convert between the binary and the decimal number systems and recognize the most commonly used binary codes. Number 4, name the major components used in implementing digital circuits and explain how they operate. Number 5, explain the operation of digital logic gates. Number 6, identify the most popular integrated circuit families used in digital equipment and discuss their operation, characteristics, and features. Number 7, use Boolean algebra to express logic operations and minimize logic circuits in design. Number 8, explain the operation of flip-flops. Number 9, discuss the operation and application of binary and BCD counters, shift registers, and other sequential logic circuits. Number 10, name the most frequently used combinational logic circuits and explain their operation. Number 11, design both combinational and sequential logic circuits for a given application from definition and concept to the selection of the integrated circuits. Number 12, discuss the operation and application of digital counters in time and frequency measurements. Number 13, explain how a digital computer is organized and how it operates. Number 14, discuss microprocessors, explain their operation, and give examples of their applications. Digital techniques are used in virtually all areas of electronics. Your success as an electronic engineer or technician is highly dependent upon your knowledge of digital methods. Your pursuit of electronics as a hobby is also directly related to your knowledge of digital techniques. This program provides you with all of the digital fundamentals necessary to help ensure your success in electronics. Digital techniques are relatively new to the field of electronics. As late as 25 years ago, digital techniques were virtually unused in electronic equipment. Although not known as digital techniques, such methods were known and understood long before this. Perhaps the earliest practical use of digital techniques occurred in the late 1930s and 1940s, where such methods were used in telephone switching and industrial control applications. All of these applications involved relay switching circuits. The electronic use of digital techniques began in the 1940s, when they were applied to sophisticated military electronic equipment. Despite the developments made during this time, only limited use was made of digital techniques in areas outside of the military. In the late 1940s and 1950s, there was a significant amount of activity in the development of digital computers. Clearly, it was the development of the digital computer that spurred the most rapid and significant growth in digital components, circuits, and techniques. As computing methods were discovered, New and improved electronic circuits were developed to implement them. First, vacuum tubes replaced relays. Then, in the late 1950s and early 1960s, vacuum tube digital circuits rapidly gave way to modern transistor circuitry. Transistors reduced the cost, size, and power consumption of a digital computer. Increases in operating speed were also obtained. Further improvements in semiconductor manufacturing techniques brought about improved transistors, and then integrated circuits. In the early 1960s, the first practical integrated circuits were introduced. Computer manufacturers rapidly adopted integrated circuits to implement their new machines. This great demand for integrated circuits lowered their cost and further stimulated their development. More recent developments in integrated circuit technology have enabled the semiconductor manufacturers to put an entire digital computer in a single integrated circuit package. Known as a microprocessor, this computer on a chip promises to revolutionize electronic equipment in much the same way that integrated circuits themselves affected it. As digital integrated circuits have developed, their cost has dropped, and more sophisticated circuits have become available. As a result, digital techniques are now used in all areas of electronics. This includes test equipment, consumer electronic products, communication systems, industrial controls, as well as computers. Digital techniques offer many benefits over analog methods. They reduce the cost and improve the performance of electronic equipment in most cases. They provide new and improved solutions to old problems and permit functions not previously possible with analog techniques to be performed. They have automated many operations, making the equipment easier and more convenient to use. Today, electronics is a digital world. The prerequisites for this program are previous formal training or experience in electronic fundamentals, a knowledge of basic electrical principles, and the operation of electronic components and circuits is essential. If you have not had such training, we recommend that you obtain it prior to beginning this course. The HEATHKIT Electronics Fundamental series of individual learning programs can provide the necessary background. To complete the hardware experiments in this program, you will need the HEATHKIT ET3200 Digital Design Experimenter. This breadboard training unit contains all of the power supplies, signal sources, displays, and controls needed, plus a convenient means of interconnecting circuits without solder. All of the components called for in the experiments are supplied with this program. In addition, you will need a DC voltmeter capable of measuring up to 15 volts. A standard 20,000 ohm per volt analog multimeter will do nicely, although vacuum tube voltmeters, transistorized multimeters, and digital voltmeters can be also used. Side 2 of this record is a complete overview of this program in digital techniques. This overview is keyed to the course outline that accompanies the course objectives in the front of your manual. Play Side 2 next for a detailed look at the material to be covered. Refer to the outline as you listen. Course Overview. Before you begin this program in digital techniques, we are sure that you will want to know exactly what you are going to learn. The course objectives presented earlier gave you a general look at the course contents. But now let's be more specific about the subjects to be covered. The entire course outline is presented on the sheets accompanying the course objectives in front of your manual. Refer to this course outline now as we give you a bird's eye view of the subjects you will learn. In the first unit, Introduction to Digital Techniques, you will learn what digital techniques are and how they compare to more conventional analog methods. You will also find out why digital methods are so popular. The benefits of digital techniques are thoroughly discussed. Then you will learn where digital techniques are used. The most important part of this unit concerns the binary number system. You will learn what the binary number system is and why it is so important to digital techniques. The binary number system is the language of all digital equipment. You will learn how to convert between the binary and the decimal number systems, and you will be introduced to many of the commonly used binary codes. In Unit 2, Semiconductor Devices for Digital Circuits, you will learn that the key element in all digital circuits is a transistor. A programmed instruction review of the bipolar transistor is given to help refresh your memory on this important subject. You will see how the bipolar transistor is used as a switch. Then you will learn how to design a bipolar transistor inverter circuit which has wide application in digital circuits. Finally, you will cover the metal oxide field effect transistor, better known as the Mosfet. This device offers special advantages over the bipolar transistor in implementing digital circuits. Unit 3, Digital Logic Circuits, discusses the basic types of logic elements. These are the AND gate, the OR gate, and the inverter. You will learn how each of these units operates and how they are used to implement digital logic functions. You will also study NAND and NOR gates. These are modified versions of the basic logic elements and are widely used in implementing digital equipment. The experiments in this unit permit you to demonstrate and verify the operation of the most commonly used logic circuits. In Unit 4, Digital Integrated Circuits, you will study logic circuit characteristics. You will use this information to compare the various types of digital integrated circuits. Most of this unit is devoted to a discussion of the most popular types of digital integrated circuits. These include transistor-transistor logic, or T2L, emitter-coupled logic, and MOS logic circuits. The two experiments in this unit allow you to demonstrate both T2L and CMOS logic gates. You will also learn how to select a digital integrated circuit for a specific application. In Unit 5, Boolean Algebra, you will learn a mathematical method for analyzing and designing digital logic circuits. You will be shown how to express logic functions in equation form using Boolean algebra. Boolean rules are then given to help you manipulate these logic equations for the purpose of analyzing and minimizing logic circuits. You will also study truth tables in this unit. A truth table is a tabular means of describing the operation of a logic circuit. The experiments in this unit reinforce what you have learned. Unit 6 covers flip-flops and registers. You will learn the three basic types of flip-flops and how they operate. You will also be given typical examples of how each of these important storage elements are used in practical digital equipment. 3 experiments permit you to demonstrate the operation and application of each type of flip-flop. Storage registers are also covered. Unit 7 is devoted to sequential logic circuits. Specifically, these are counters, shift registers, and clock circuits. You will learn what a binary counter is and how it is used. The various types and classifications of counters are given. Several experiments are devoted to the demonstration of typical counter circuits. You will also study shift registers in this unit. 2 shift register experiments help you to demonstrate shift register operation and application. In the latter part of this unit, you will study clocks and one-shots. A clock is simply an oscillator circuit that is used to drive digital logic elements. A one-shot is a circuit that generates a fixed duration output pulse. These circuits are useful in performing a variety of timing and sequencing operations. Unit 8, Combinational Logic Circuits, describes the operation and application of all of the most widely used combinational logic circuits. These include decoders, encoders, multiplexers, demultiplexers, and the exclusive OR. In the experiments, you will demonstrate the operation of each of these important circuits using modern MSI circuits. You will also study read-only memories, or ROMs, in this unit. You will see how they operate and how they are used. The unit concludes with a discussion of programmable logic arrays. In Unit 9, Digital Design, you put all of your knowledge of digital techniques together and learn the process of designing digital circuits for specific applications. This unit outlines a basic design philosophy and specific procedures that you can follow to define and develop both combinational and sequential logic circuits. Numerous design examples and practice problems are given to help you learn this important subject. Unit 10 covers digital applications. While digital techniques are used in many ways, we concentrate on specific examples that are representative of typical digital equipment. We use these examples to help you consolidate and review the material you have learned in the program. In the first part of this unit, the digital counter is discussed. A digital counter is an electronic test instrument used for measuring time and frequency. The operation of a typical counter is analyzed in detail. The unit concludes with a discussion of digital computers and microprocessors. No course on digital techniques would be complete without a discussion of this important subject. Digital computers are widely used in implementing digital equipment. The microprocessor, which is an integrated circuit digital computer, promises to revolutionize digital equipment. Many hardwired digital logic circuits are being replaced with low-cost microprocessors. In this unit, you will learn what microprocessors are and how they are used. A discussion of programming techniques gives you the basic skills for using these important devices. Review the course outline thoroughly, then begin your studies. Start with Unit 1. Follow the directions in the unit. Unit 1, Introduction to Digital Techniques. In this first lesson of your individual learning program, you're going to learn what digital techniques are and how they are used. You will learn the difference between digital techniques and the more conventional analog methods. Then you will see some typical applications for digital techniques. The greater part of this lesson is devoted to a discussion of the binary number system. Binary numbers are the basic language of all digital equipment. The binary number system is a set of rules and procedures for representing and manipulating numerical quantities with just two digits, 0 and 1. It is much simpler than the decimal number system, where quantities are represented with the 10 digits 0 through 9. Your understanding of digital techniques is based directly on your ability to handle binary numbers. To prepare you for the material on the binary number system, let's review the decimal number system briefly, and then introduce you to the concept of representing quantities with binary numbers. Refer to the sheet of figures labeled Illustrations for Audio Record 3, Side 1 in the front of your manual. The decimal number system is a method of communicating numerical information by using the 10 digits 0 through 9. By combining these digits in a variety of ways, we can represent any quantity. Refer to Figure A in the illustrations. Here we show the 4-digit decimal number 6,394. Each of the digits in the number has a certain position, and that position determines its weight. The position weights from right to left are units, tens, hundreds, and thousands. The digits in each position of the number and their weights tell us the value of the number. For example, there are 4 units, 90 tens, 3 hundreds, and 6 thousands. When we add these four quantities together, we arrive at the original decimal number as shown in Figure A. The binary system is similar to the decimal system in that the position of a digit in a number determines its weight and, as a result, the ultimate effect that it has on the quantity being represented. The difference between the binary system and the decimal system is the number of digits used. In the binary number system, only 2 digits are used to represent quantities. These binary digits, or bits as they are called, are 1 and 0. Refer to Figure B. Here we show that the 5-bit binary number 10110. Above each bit is a number representing the weight of that bit position. The weights in the binary number system from right to left are 1, 2, 4, 8, and 16. Each successively higher position weight is twice the value of the previous position weight. Figure B shows how the 5-bit binary number can be converted into its decimal equivalent. All you do is add together the weights of those positions containing a binary 1. Binary 1s appear in the 2, 4, and 16 positions. Adding these weights together gives us the decimal equivalent 22. By using the appropriate number of bits, any decimal quantity can be represented. Figure C shows a table of 4-bit binary numbers and their decimal equivalents. Study the table and mentally convert each binary number into its decimal equivalent by adding together the weights of those positions containing a binary 1. The binary number system is easy to use once you become familiar with it. It may be confusing at first, but with a little practice, you should have no difficulty in converting between the binary and decimal systems. Detailed procedures for making these conversions are given in the lesson unit. The reason for using the binary number system in digital equipment is the ease with which it can be implemented with electronic components. Components and circuits with 10 states to represent decimal numbers are complex, costly, and impractical for most applications. An electronic component or circuit with only 2 states is required for each bit in a binary system. Such components and circuits are simple and inexpensive. For example, a single-pole, single-throw switch can be used to represent 1 bit of binary information. An open switch may represent a binary 0, while a closed switch may represent a binary 1. An indicator light can also be used to represent binary information. An off light might represent the binary 0 state, while an on light would represent the binary 1 state. Binary switches and lights are widely used to represent binary data in modern digital systems. Figure D shows a set of toggle switches used to enter binary numbers into a piece of digital equipment. When a switch is in the down position, it represents a binary 0. When a switch is in the up position, it represents a binary 1. Study the set of switches in Figure D and convert the binary number presented there into its decimal value and record it in the space provided. If your answer is the decimal number 37, you are correct. The switches with weights of 1, 4, and 32 are in the up position, indicating the binary 1 state. Adding together these weights gives us the decimal equivalent of 37. Figure E shows how indicator lights are used to represent binary numbers. When the light is on, it represents a binary 1. When it is off, it represents a binary 0. Study the indicator lights in Figure E and determine the decimal value being represented. Record your value in the space provided. The lights with weights of 1, 4, 8, and 16 are on in Figure E. Adding together the weights of these bit positions gives us the decimal value of 29. By using the 4 data switches and 4 logic indicators on your HEATHKIT ET3200 Digital Design Experimenter, you can implement binary numbers with hardware and practice converting binary numbers into their decimal equivalents. Simply use 4 pieces of hookup wire to connect data switch SW1 to logic indicator L1, SW2 to L2, SW3 to L3, and SW4 to L4. Turn on the Digital Design Experimenter. Then, set the data switches to the desired binary number. You will see that the binary number displayed by the logic indicators corresponds to that set with the data switches. Using Figure C as a guide, set the switches to the binary numbers in the table and observe the logic indicators. Mentally convert each binary number into its decimal equivalent. Despite the simplicity of this exercise, you will find it very valuable in learning the binary number system. You should memorize the binary numbers shown in the table of Figure C and their decimal equivalents. This knowledge of binary numbers will greatly enhance your ability to understand the digital circuits to be described later in the program. Now refer to the Unit Activity Guide in Unit 1 and continue with the text material. Unit 2, Semiconductor Devices for Digital Circuits. All digital circuits are made up of binary or two-state electronic components. These components process the binary data. A variety of two-state devices are used in digital equipment. These include mechanical switches, indicator lights, relay contacts, and magnetic cores. However, the most commonly used binary device is the transistor. All modern digital circuits use these versatile semiconductor devices. Early digital equipment was made up of discrete component digital circuits constructed with individual transistors, resistors, diodes, and capacitors. But today, most digital equipment is built with integrated circuits where entire logic networks are constructed in micro-miniature form on a single silicon chip. The basic component of an integrated circuit is, of course, the transistor. Refer to the figures in the front of your manual labeled Illustrations for Audio Record 3, Side 2. The transistor most often found in digital circuits is the bipolar transistor. The bipolar transistor is a 3-element semiconductor device that is used to control the flow of an electrical current. Refer to Figure A, which shows the general physical structure of a bipolar transistor. The 3 elements of this device are the emitter, the base, and the collector. These 3 elements are made up of P and N-type semiconductor materials that form 2 p-n junctions. These junctions are biased by external voltages to produce the desired operation. The path for current flow through a bipolar transistor is from the emitter through the base to the collector as shown in Figure B. The magnitude of the current flowing through the transistor is a function of the external applied voltage and any series resistance. The current flow through the transistor is also determined by the amount of external voltage applied to the base. By varying the base current, The current between the emitter and collector can be controlled. Only a small base current is required to control a large emitter-collector current. This means that the transistor has gain. Figure C shows the schematic symbol used to represent a bipolar transistor. In processing analog signals, transistors are used primarily for amplification. A small input signal is converted by the transistor into a larger output signal. When used in this manner, transistors are known as linear devices. Their output is an enlarged version of the smaller input. In digital circuits, the transistor is not used in this way. Instead, the transistor is used as a switch. The bipolar transistor is an excellent switch that can readily take the place of mechanical contacts. To be used as a switch, the transistor assumes one of two states. These states are cutoff and saturation. When the transistor is cut off, no current flows through it. Therefore, it acts as a very high resistance or open circuit. When the transistor is saturated, it is conducting. A substantial amount of current flows through the transistor in this state, and it represents a very low resistance or closed circuit. By controlling the amount of current applied to the base element, the transistor can be made to switch rapidly between cutoff and saturation. High-performance transistors in digital circuits can be switched on and off in a few nanoseconds. Remember that a nanosecond is 1/billionth of a second. Such transistors permit logic circuits to operate at very high speeds. High operating speed is a desirable digital circuit characteristic. Another transistor widely used to implement digital circuits is the metal oxide semiconductor field effect transistor, or Mosfet. The Mosfet, like the bipolar transistor, is a three-element semiconductor device used for controlling the flow of an electrical current. It has three elements designated the source, the gate, and the drain. The symbol used to represent a Mosfet is shown in Figure D. Current flows through the device from the source to the drain. The amount of current flowing is a function of the external voltage and resistance. The gate element is also used to control the amount of current flowing through the device. The Mosfet is an excellent switch. A voltage applied to the gate element turns the Mosfet off and on to represent the binary 0 and binary 1 states. The Mosfet used in digital circuits is a normally off device. When it is off, it appears to be a very high impedance or open circuit. When a gate voltage of a certain magnitude is applied, the transistor conducts and acts as a very low resistance or closed circuit. An advantage of the Mosfet over the bipolar transistor is that it is simpler to construct and it occupies less space. This means that more of these devices can be constructed in a given area than an equivalent number of bipolar transistors. This makes Mosfet circuits smaller and less expensive than bipolar circuits. In addition, the high impedance nature of the Mosfet means that MOS circuits have a very low power consumption compared to their bipolar counterparts. Minimum power consumption is a desirable characteristic of any electronic circuit. The primary disadvantage of the Mosfet is its slow switching speed. The bipolar transistor can switch in a few nanoseconds, but it takes the Mosfet a few hundred nanoseconds. For many applications, very high speed is not necessary. Mosfets are widely used where low speed and low power consumption are the most desirable characteristics. The Mosfet is the basis for most large-scale integrated circuits. Complete circuits and systems can be manufactured within a single miniature package instead of interconnecting individual digital circuits. The small size and simplicity of construction of the Mosfet makes such high-density, sophisticated circuits a reality. Bipolar and MOS field effect transistors are used the same way in all digital circuits. Both types are used to switch the supply voltage. The two switch states, off and on, create two voltage levels, which are used to represent the binary 0 and binary 1 states. In this unit, you are going to review the operation of the bipolar transistor. You will then learn how the bipolar transistor is used as a switch. Its characteristics will be discussed in detail. Then you will learn to design bipolar transistor switching circuits. The basic bipolar transistor logic circuit is called an inverter. You will be given a procedure which shows you how to select a transistor and calculate the component values necessary for a specific application. In an accompanying experiment, you will actually design, construct, and test a bipolar transistor inverter circuit and verify its operation. Finally, you will study the Mosfet. The various types will be considered and their characteristics discussed. Now check your unit activity guide for the next step in proceeding with this unit. Unit 3, Digital Logic Circuits. In this unit of your HEATHKIT individual learning program, you're going to study digital logic circuits. Logic circuits are the basic building blocks of all digital equipment. These basic circuit elements are combined in a variety of ways to form functional blocks that perform specific digital operations. These functional blocks are then combined to make up complete instruments and systems. This entire program emphasizes digital circuits and their application. As an engineer, technician, or hobbyist, your interest in digital techniques lies in the operation and use of digital logic circuits. This unit forms the basic foundation upon which all future units are built. You will use the fundamentals presented here throughout the rest of the program and in your future work with digital techniques. It is especially important for you to learn this material thoroughly. Logic circuits are those elements that are used to process and manipulate digital signals. Logic circuits work with binary numbers. They accept binary inputs, process these inputs, and then generate binary outputs appropriate to the application. There are two basic types of digital logic circuits: decision-making and memory. Decision-making logic circuits accept binary inputs and generate one or more outputs that are a function of the binary input levels and the type of logic circuit. This type of logic circuit monitors the states of the input signals, makes a decision regarding these inputs, and generates the proper output. Memory circuits are used to store binary data. In many digital applications, it is necessary to remember previous binary states or to store binary numbers. Most memory elements store a single bit of binary information. The basic decision-making logic circuit is called a gate. Gates have two or more inputs and a single output. The output is a function of the input states and the specific processing characteristics of the circuit itself. Gates are then combined in various ways to form larger, more complex logic networks known as combinational circuits. Combinational logic circuits perform decision-making operations of a more sophisticated nature. Typical combinational logic circuits include encoders, decoders, multiplexers, demultiplexers, comparators, and arithmetic circuits. The basic memory logic element is known as a flip-flop. A flip-flop stores a single bit of information. The flip-flop circuit has two stable states, one which represents a binary 0 and the other which represents a binary 1. The flip-flop can be put into either of its two states so that it remembers the bit being stored. Binary signals are applied to the flip-flop inputs to change its state in the desired manner. The flip-flop outputs indicate the state of the flip-flop or the value of the bit stored there. Flip-flops are generally combined to form storage registers, counters, and shift registers. Such circuits are known as sequential logic circuits. Sequential circuits are a class of logic networks that contain memory and perform logic operations of a time-based nature. Storage registers are used to remember a binary number or word over a long period of time. Counters monitor a particular binary level and count the number of times it occurs. In this unit, we concentrate on gates, the basic decision-making logic element. Flip-flops will be covered in a later unit. Now, let's consider these decision-making circuits. Refer to the figures in the front of your manual labeled Illustrations for Audio Record 4, Side 1. There are three fundamental decision-making logic circuits. These are the AND gate, the OR gate, and the inverter. The AND gate is a circuit that has two or more binary inputs and a single output. The symbol used to represent an AND gate in logic circuits is shown in Figure A. The gate is designed to generate a binary 1 output only if all inputs are binary 1. If one or more inputs are binary 0, the output will be a binary 0. An OR gate also has two or more inputs and a single output, but it is designed to generate a binary 1 output if any one or more of the inputs is binary 1. If all inputs are binary 0, the output will be binary 0. Figure B shows the logic symbol for an OR gate. The inverter has one input and one output. The output of the inverter is always the opposite or complement of the input. That is, if the input is binary 0, the output will be binary 1. Or if the input is binary 1, the output will be binary 0. You may sometimes hear the inverter called a Nought circuit. Refer to Figure C. All digital circuits, both combinational and sequential, can be constructed with just these basic elements or some variation of them. The most commonly used variations are Nand and NOR gates. The Nand or not AND circuit is simply an AND gate followed by an inverter. The NOR or not OR circuit is an OR gate followed by an inverter. Both NAND and NOR gates can be used to implement any digital circuit. The NAND and NOR logic symbols are shown in Figures D and E respectively. To back up the text material on gates, you will perform three interesting experiments in this unit. You will build and demonstrate an inverter in Experiment 2. In Experiment 3, you will construct and test diode and OR gates. Then, in Experiment 4, you will build a discrete component, transistor NAND NOR gate, and verify its operation and characteristics. Turn now to the Unit Activity Guide and continue with this unit.